All right. Well, hello, everyone. Good morning, good afternoon, or good evening, depending on where you are connecting today. And welcome. Welcome to this webinar, Why CSP is a Missing Piece in California's 100% Clean Energy Puzzle. My name is Christina Galan from ATA Insights, and I will be moderating this webinar today. If you have, I'll do a couple of housekeeping rules before we start the webinar. It will be 1 hour of duration, and we will first go through the slides, and then we will have a Q&A session afterwards. So if you have any questions and you're connecting on Zoom, please use the Q&A box right below. And if you are connecting on YouTube, you can use the chat. So also, just so you know, the webinar is being recorded and it will be sent to you alongside the approved slide deck of the panelists in a couple of days. You also have a chat there, so please use it, introduce yourselves, let us know a little bit more about you, where you're coming from, and why you're interested in CSP. We have an amazing panel today with amazing speakers. So I'm going to start with John White from CEERT. John, good morning for you, right? Yes.
Good morning.
All right. Well, I'm going to start sharing my screen so we can see the slides. Let me know when they're up. All right. I think they are ready. Can you see them?
Okay. Welcome, everyone, and thank you for coming. We have an extraordinary group of people both listening as well as presenting, and we're very, very happy that you could join us. I want to first acknowledge that this work has been supported by the Department of Energy through the National Renewable Energy Laboratory, but the views expressed in this webinar are those of our own and are not necessarily those of the Department of Energy. We have to present to us today, we have Fred Morse from Soltor and Morse Associates, longtime expert on concentrating solar power. Hank Price with SolarDynamics, also a longtime global leader on concentrating solar power. And then Alex Zolan with the National Renewable Energy Laboratory. And Allison Lenthall with Lenthall Advisors, which has done some public opinion work. So the next slide is the agenda, I believe. And so we're going to talk about SB 100, the California law that requires 100% clean energy by 2045. And then discuss the current global landscape of CSP. CSP hasn't been developed in recent years in California, but there has been an enormous amount of activity globally that influence our confidence about this technology now. And then describe the element of our project. We've had a stakeholder advisory committee as we've developed these results. And so we've had good outreach already. And then we'll talk about what the NREL modeling results tells us and comparing the value of CSP compared to other technology. And then finally, the public opinion research on support and interest in concentrating solar power and other technologies. Next slide. So SB 100 requires 100% clean energy by 2045 and 60% are renewables by 2030. We've made good progress so far, but there's much to be done. The challenge is associated with increasing load growth, especially due to increased electrification, climate change, and digital infrastructure. The other issue for us is maintaining reliability and addressing the evening peak when PV solar drops, especially in the summer months. And this need for firm, clean generation in the evening hours is a principal value of CSP. Next slide, please. So the one of the requirements of SB 100 is that the agencies had to develop a joint report on the pathways to achieving that target. And historically, CSP hasn't been included among the technologies because the cost analyses are outdated, particularly given the growth in the global market and supply chain, as well as earlier environmental concerns, particularly about avian mortality with a particular design of CSP. Recent advancements have significantly reduced these concerns and warrant reevaluation of how modern CSP with thermal energy storage systems can offer firm, dispatchable, clean energy at an affordable cost. The role of CSP in achieving SB 100 goals, including its inclusion in resource planning, modeling scenarios, and transmission development strategies, is an important next step that we hope this presentation will help answer. And particularly, what could the role of CSP and thermal energy storage be in California's clean energy portfolio, and how can we use CSP and thermal energy storage to enhance reliability and affordability? So to give us some recent knowledge about the deployment of CSP across the globe, I'm going to hand it to Fred Morse now.
Thank you, John. Quick word of introduction. I'm currently the CEO of Solstar Energy, a CSP development company in the US, formerly senior advisor for Abengoa and involved in the development of Zolan and Mojave, two plants I'll mention in a moment, and former head of the US Department of Energy's Solar Thermal Energy Research Development Demonstration Program. So let me give you some update on CSP. The commercial status of CSP in the United States can be viewed in three phases. The first phase was triggered by PURPA, a federal law that was supposed to stimulate renewable energy projects, and the California standard offers, and they were looking for energy. So 1984 to 1991, 9 SEGS plants, trough plants were built in California, and they operated well through their 30-year lifetime. Phase 2 was triggered by the Renewable Portfolio Standards, which asked for carbon-free energy. And in 2006, Nevada Solar One, a trough plant, came online. And in the years 2013 to 2015, 5 large CSP plants came online, 2 in California, 2 trough plants in California, and 1 tower plant in California. And in Arizona, a trough plant with 6 hours of storage, and in Nevada, a molten salt tower with 10 hours of storage. Phase 3 is being triggered by the demand. It's not enough to be carbon-free. It has to be dispatchable. And SB 100, which John White mentioned, is an example of what is driving Phase 3. And CSP, with its long-duration energy storage, can provide reliable, dispatchable power, day or night, cloudy or bright, and to handle a sequence of cloudy days in a row by the use of a green fuel or natural gas burner, it can do that every day of the year. So the technology has improved through each of these phases. Next slide is a picture of a trough plant. This one is in Dubai. You can see the field of troughs, and in front you can see the storage tanks. On your right is the typical schematic in 3 sections. The solar field is on the left of the sketch. In the middle are the storage system, tanks, and on the right is the power block. The next slide shows you a molten salt tower, and that's the Crescent Dunes project. And the schematic is very similar, except the solar field looks a little jazzier. Next slide. Let's take a look at the globe. You'll notice that there are only a little more than 8 gigawatts of CSP to date. And they're operating throughout the world. Every inhabited continent has them. Most of the activity these days is in China, but CSP has been operating reliably for more than 4 decades around the world. Now let's take a look at China because it's quite interesting. Next slide. China leads the world in PV and battery manufacturing, so you would think they would just build PV and batteries to meet whatever energy need they have. But they're not. They have 13 molten salt towers operating. They have 19 currently under construction, 20 more announced. And they require any renewable energy project has to have some storage, and they require a minimum of 10%. And in the desert regions, they will do that with CSP. So the United States has a similar need, and we have a need to augment our daytime PV with CSP so that we can provide energy 24 hours a day. Next slide, and my last slide, is with the map in your mind, there are a lot of projects shown on that map. And about 7 years ago, the Department of Energy said, you know, there's a lot of good information out in those projects. Why don't we find out what issues did they run into in the design, construction, startup, and operation? How did they solve them? And even more importantly, how could they have avoided them? And all of that information was put together in the best practice report that you see on your right. And we basically learned there aren't many technical issues facing the trough and the tower projects. Yeah, some challenges with the hot tank and transients, but our findings were that with appropriate engineering, good equipment, and in particular, people who know what they're doing, good EPCs and the owner's technical specs being right, we concluded that future tower and trough plants can be built on time and perform reliably. So California should not have any worries that future plants that are built to serve their need will perform properly. And I'll turn the mic over to Hank.
Thanks, Fred. I'm Hank Price. I've been working in CSP for 40 years. I started at the SEGS plants as a plant engineer, worked at NREL doing systems analysis for a number of years, then worked with Abengoa Solar during their US development when they built their Solana and Mojave plants. And then the last 10 years or so, I've been working with SolarDynamics, where we've been working on next generation CSP technologies and plant configurations. I'm the principal investigator on the study. First off, I want to thank Fred, John, and other members of our team, Alex and Allison, that are here to present, but want to thank everybody for all their contributions to this effort. So the question is there a role for CSP in California? And our study has sort of 4 points. The first point we're looking at is we're doing a technology assessment to identify which CSP configurations could best meet California's future energy needs. The second point is looking at where CSP plants might be developed. Then trying to understand how cost is a sensitive driver. How can we develop CSP plants most cost effectively and improve the overall performance of the plants? And then finally is an outreach. There's not a lot of information seems to be getting out about how CSP is actually doing around the globe. And so a key part of this activity is stakeholder outreach, especially to California stakeholders, to try to get them informed about the potential of CSP technology. Next slide, please. Probably most everybody on the call is familiar with the California duck curve. This shows the worst case hourly net system load for California over the past a dozen years or so. And over time, the belly of the duck has been getting closer and closer to zero. And so the question is, how can CSP help California? Next. So the premise here is that CSP can be designed to supply power in the evening and through the night when California needs to cover their load, which isn't being, which wouldn't normally be covered by PV. Next slide. So this shows that this is a forecast out into 2035. And this shows that we can see that each month of the year down the left side and hours of the day, red are periods when the system needs more power. Green is less power. So during the day, they have less demand for power that can generally be met by photovoltaic power. But all through the year, there's a demand for power at night and in the evening and through the night. So CSP potentially could be a good option for California's future energies needs. Next slide. So I mentioned we did outreach, stakeholder outreach in California. We have a group of participants coming from many of the state agencies, the PUC, the Energy Commission, the Independent System Operator, utilities in the state, and other stakeholders representing environmental interests and renewable energy interests and developers. So we had a group of about 25 people, and we did a survey to get their input on their perceptions of CSP. And so I'm sharing some of the results from that, and it shows which, from a technology issue, what do people consider the most important issues? And so cost and performance is generally the key concern with CSP. In terms of siting, access to transmission is a huge concern, and then also availability of suitable siting, land for siting of plants. So we use this survey results to help us determine what activities we needed to conduct and what questions need to be answered for California to be comfortable with the technology. Next. So first step is looking at the technology. We looked at sort of the commercial conventional CSP technology, oil troughs, and molten salt tower. But the technologies have to have thermal energy storage to be relevant. So it's oil trough with indirect thermal storage and molten salt tower with direct thermal storage. We looked at other advanced technologies. New distributed tower technologies are being developed that hold promise for cost reduction and other important attributes to improve flexibility of operation. We looked at molten salt trough technology, and also there's Gen 3 technologies that DOE is developing that have potentially even lower costs than current technologies. But none of the advanced technologies are really commercially ready. So we selected the molten salt tower as the technology we were going to look at for this study. It represents currently the lowest cost and has low cost thermal energy storage, which allows a high level of dispatchability such that plants can be built to be either base load or designed for nighttime generation, nighttime dispatch. We also looked at hybrid configurations, primarily CSP hybridized with PV, so using PV during the daytime and CSP at night. And as a reference, we're comparing to photovoltaic with battery energy storage as sort of the alternative for cost comparisons. Next slide. This is a chart that shows the capacity factor for a plant, CSP molten salt tower plant, with a large amount, 14 hours of energy storage. And basically, this is a configuration shows that, for each month of the year and hour of the day, that energy can be collected during the day and dispatched at night. And so you can achieve with this configuration, you can achieve a high capacity factor in the evening and through the night. Next slide. So in terms of costs, the first two bar charts here are PV plus batteries. We looked at, we're using NREL's ATB for cost information. We looked at both the 2025 costs and 2030 costs because we all know the cost of PV and batteries is continuing to drop in price. So just for a reference, we want to make sure we are aggressive enough in terms of what the cost targets are that CSP needs to compete against. The next two bars show CSP baseload plant. These are all for configurations that achieve a 75% annual capacity factor, so more or less a baseload configuration. But we can see that a standalone CSP plant using today's technology cost assumptions should be competitive against PV and batteries. And by building a 4-plant power park, you can further reduce the cost by about 20%. Also, hybridizing with PV can help reduce the cost as well. So both standalone and hybrid CSP plus PV plants, should be more cost competitive than just PV and batteries alone. Next slide. The other area we focused on is looking at where to site future CSP plants. And so we used a process similar to what the California Energy Commission has done, looking at resource potential for utility scale photovoltaics and also for wind generation. We adapted their approach a little bit. First, screening. The basic process is you sort of create a grid across the state and you exclude areas that are not suitable for development. And so we followed a similar approach, but we adapted this to account for the unique differences of CSP plants. Primarily, we added larger buffers around population centers and airports. We eliminated areas that have military training routes above them, and any areas in the desert, any areas that had existing residential or commercial buildings, and also required a minimum size of a 1.5 miles by 1.5 miles on a side, which is sort of a minimum size for a full-scale molten salt tower plant. The other thing we did is a big part of this is screening lands for environmental and land uses. When the Energy Commission did their analysis, they pretty much eliminated all of the desert lands. Desert lands are really prime siting locations for CSP. So in our study, we left in some of the areas in green shown on the figure here for at least for consideration of potential siting of CSP plants. Next slide. So this shows the end results of where we looked at siting of CSP plants. The green areas are areas that use the more restrictive environmental screens that the CEC used. The red areas are additional ones that we added back in based on our less restrictive screening of the desert areas. And basically what you see is there's almost no green areas in the desert. But when we take a little more liberal approach to where we might build plants in the desert, we add quite a bit of additional land. Now you'll notice there's a lot of land in the California Central Valley. The green areas kind of up to the top and left. The middle areas are the in red are really the desert regions in California. Next slide, please. So when looking at the sites, it's important to also consider the economic assessment of those sites. So it's not just where land is available, but where the most cost-effective sites are going to be. So we conducted an economic assessment where for each site we look at adjust for the solar resource, any regional cost differences, distance to transmission, the remoteness of labor, potential wheeling charges, as well as whether it's within an energy community that might allow it to qualify for an additional 10% ITC adder. So next slide. And so this summarizes the results of our study. The circles here represent each of the sites we identified. The size of the circle identifies the gigawatt capacity of potential siting of CSP plants. So this would be siting of a baseload CSP plant. And the color represents the cost, the levelized cost of energy, where green are the lowest cost options and red are the higher priced siting options. And so what you see circled in green or in red there, the green dot circled in red is an area in the Mojave Desert near the existing SEGS plants, where there's significant potential for 5 to 10 gigawatts of siting of molten salt tower technology. You'll note the Central Valley, even though there's more siting potential, those are the red circles up to the left. Due to the lower solar resource, the price is quite a bit higher there. But you also notice there's a lot of green out in Arizona and New Mexico. So there's a large potential for supplying CSP power from both Arizona and New Mexico. Okay, that completes sort of my portion. Alex Zolan will talk now about NREL's capacity expansion modeling that they did for California. Thanks.
Thanks very much, Hank. My name is Alex Zolan. I'm a researcher at National Renewable Energy Laboratory. I've been working on CSP research for a little bit under a decade, focusing on techno-economic analysis, some systems analysis, and just general design and dispatch optimization for CSP power plants and other plants as well. And what I'll be talking about is work that also was largely led by Chad Augustine and Sarah Awara, who were also at NREL. On the next slide, I'll present some of the assumptions of the capacity expansion study that we conducted, which was using the regional planning model, or RPM. This is a consistent model with what was done in the LA 100 study, for those who might be familiar with that, which for a smaller region than California, we're looking at achieving 100% renewables. We adopted a lot of similar cost assumptions that you heard earlier from Hank, in the sense that we use the same source, the 2022 Annual Technology Baseline, or ATB. This does include, present day costs as well as forecasted costs all the way out to 2050. And so when thinking about the longer duration of a capacity expansion model, we have those costs and those forecasted costs covered as well for all technologies. And we were trying to focus in on the higher priority development areas that Hank had alluded to, the Central Valley, Mojave Desert, Imperial Valley. And so we leveraged one of the features of RPM, which is allowing us to have nodal fidelity or higher spatial fidelity within some of the network, and then lower fidelity, which is basically balancing area roughly level fidelity in the rest of the Western Interconnection, which is kind of shown by what's inside the black squiggle on the left and outside the black squiggle on the right. So that's a sense of what we were trying to evaluate. And capacity expansion models come in many different sort of flavors, but again, like I said, we have some reference points previously for this one. This one does include transmission level planning as well. And on the next slide, we have the results. or at least the starting part of the results. We started by trying to replicate as close as possible the CEC Joint Agency report, which didn't include CSP, and then we more or less added the CSP technology afterwards, after updating for things like the modern cost assumptions at the time. And if we just look at these very large stacked bar charts with lots of colors, which I'll say maybe don't focus on them a whole lot, with the exception of perhaps that bright orange one, the CSP stack, which is about halfway through. And when you include CSP and you make your way out to 2045, we see that there's gradual deployment of CSP from 2030 to 2045 to the tune of 9 gigawatts of capacity. This represents about 6% of the total capacity in California under that scenario. Again, to get into a little bit more detail in terms of what's being displaced, it's better to look at a difference chart, looking at the difference between those two scenarios, and you'll see that on the next slide. And here we see that with the RPS increasing the required fraction of renewables, that tends to be the competition economically for CSP. And so in terms of what's being displaced from a capacity standpoint, it's utility scale PV, land-based wind, a little bit of offshore wind, and battery storage composes the vast majority of what's being displaced there. We'll notice that 9 gigawatts of CSP displaces about 3 times the capacity of the wind and the PV and the batteries. A little bit of that is due to the double counting of storage, since CSP is paired with thermal energy storage and we're treating it as one factor. But even removing that, we see quite a bit of difference. And the real reason that we're seeing that difference is the higher capacity factor of these plants, because they do come with significant thermal energy storage, and so they're able to run for a larger portion of the day. The next slide moves from power capacity to generation. So this is how much energy is being generated by each plant. And the CSP fraction of that actually grows, again, because it's a higher capacity factor as compared to the renewables, which are, as you get to 2045, a much more significant portion of that technology mix from a nameplate capacity standpoint. We actually, despite being 6% of the capacity, is closer to 15% of the net generation in the state. One other thing that we'll note as we get to the difference chart on the slide that follows is that in addition to the energy displaced, which is going to come from those same sources that you saw from the capacity chart, it's largely wind and PV. And then, in addition to storage, you'll see some storage losses difference there, which are on the next slide, Christina. Thank you. You'll also see that there is about a 2 terawatt hour difference in what is generated in state versus imported from out of state. So we're seeing a little bit more net generation in California for roughly the same system-wide costs, which is, I think, I would argue, is a nice result, at least for California. The slide that follows this has some dispatch scheduling. And if I am installing a new plant and we think about what Hank had just presented, in the sense that the peak demand is happening in the early evening hours, the late evening hours, that tends to be where the highest average cost is going to be. So if I'm a plant operator and I have access to thermal energy storage, I'm going to want to prioritize those hours. And that's what we see in these dispatch figures. If we look toward that later part of the evening, or in the early evening, we're going to see sort of where that, I guess, the neck of the duck curve, if you will. That's where CSP is ramping up production every day in all of our representative days, and it sort of continues into the night. One exception to that might be where you have peak resources and peak demand, which is in the fourth one from the left. And we see that we're almost operating close to a base load plant. But largely otherwise, we see charging happening during the day, which makes sense. That's sort of in the belly of the duck, and that's the least valuable hours for a CSP plant. And then we start to see the production ramp up after that, and as we get into the evening hours and those higher value hours. So that's twofold. One, that's just showing the economic dispatch for CSP, but also showing that it's capable of delivering in those more high value hours for California. The next slide follows and just gives a summary of what configurations we modeled. So we didn't include anything without thermal energy storage. We didn't consider that to be a priority. It wouldn't be economically competitive with PV, and it'd have a very similar production profile. So those are excluded. What we varied instead was two things. One is the number of hours that you have of storage, which would just be if I'm running my turbine at full capacity, how many hours can I run it for if I have no production and a full tank of storage in my hot salt tank? And we also vary the solar multiple, which roughly could be translated to the following. If I know how much thermal energy is required to run my turbine at capacity for 1 hour, and I know the maximum capacity of what I can generate using my solar field, that ratio, or rather the inverse of that ratio, is roughly my solar multiple. So said another way, with this solar multiple 3 and 12 hours of storage, when I'm producing the peak thermal energy to be used later or sent to the turbine immediately, I get about 3 hours of turbine capacity worth of energy during the maximum production of sort of that thermal collection system. And I might be, as an example, running the turbine at full capacity and maybe storing those other 2 hours worth of energy in my hot salt tank for later use. The next slide will actually show a summary of the build out. I won't spend too much time on this other to say there's a lot of time spent or a lot of deployment happens in the Central Valley, the Mojave Desert, and the Imperial Valley. Those were sort of prioritized as, using Hank's techno-economic analysis. We saw that those were priorities. Outside of the state, we still see another 4.5 gigawatts of CSP within the capacity expansion model. Although, again, referring back to Hank's analysis, we didn't see a lot of deployment in Arizona or New Mexico, despite that those seem to be good opportunities. Our assessment of why that's happening is Arizona has a very low RPS target, and New Mexico has very good wind resources in similar places. And so in one case, we just don't have the requirement. In the other, we have there's economic competition from wind plus batteries, we believe. We also know that the results are sensitive to price. As you increase the price, as shown by the table on the bottom right here, that deployment does decrease. But even in the higher price scenario, we still see deployment in California to the tune of 2 gigawatts or so, which is still a pretty notable contribution to the total portfolio. And so we wrap up on the final slide. Again, we saw that CSP does show results in the capacity expansion model that we presented. And that's just using, current cost projections using NREL's ATB. It represents about 6% of generation capacity, but about 15% of net generation. So higher capacity factor plants. And the use of thermal energy storage allows us to prioritize the higher value hours of the day for when CSP is dispatching. So the dispatchability of CSP with thermal energy storage does show some value to the California grid in this setting. And so with that, I'll wrap up. Thank you. And I'll hand things over to Allison.
Thanks, Alex. My name is Allison Lenthall, and I'm with Lenthall Advisors. I'm a community engagement firm. I have more than 10 years of experience in communication and public relations, including about 4 years with Abengoa Solar. And on this project, I was gathering the public's opinion about CSP in Arizona, Nevada, and California. So the intention was to really learn what people's concerns were and what they thought about the CSP technology. We went to Ivanpah and California and Tonopah, Nevada to inquire about the tower plants. Also in California, we went to Silver Lakes to a community that was more experienced with the parabolic trough plants. And then we also went to Barstow, California. This is an area that doesn't necessarily have direct exposure. There's not a plant in the direct area. However, it could serve as a proxy for future areas of development. Next slide, please. We decided to focus on Tonopah, Nevada for learning what the public opinion about solar power towers is. And there's a lot of information here. I'm going to summarize it, but you'll receive the slides later. So first, we had some direct interviews with the town manager, as well as some residents of the town to better inform our questions. And then we spent 2 days conducting a written survey. The survey was actually based on the Lawrence Berkeley National Labs large-scale solar neighbors survey. And the key results could be summarized as 80% of everyone who responded had either positive or a neutral opinion about crescent dunes. The majority were not concerned about the aesthetics of the tower and the near field, and 10% more actually rated them as pleasing. They were pleasing to the eye rather than objectionable. The majority of the people who answered our survey said they would support or strongly support future solar development in the area. Now, the primary concerns were avian mortality. There was a perceived broken promise about hiring locally, construction and operation challenges, and the general lack of communication from the plant operators. Next slide, please. We also extended our inquiry to the airports closest to the towers and those within the flight path. As we knew, there had been some complaints about solar glare from Ivanpah. However, what we learned is that once the FAA added Ivanpah to the VFR aeronautical chart, the complaints subsided. We actually spoke with an Army helicopter pilot who regularly flew past Ivanpah. And really, once the pilots learned to navigate within the air path with the solar glare, and if they knew it was there, it was no longer an issue. Next slide, please. So in order to look at the public opinion of the trough plants and also looking into California to a community that hasn't had a CSP plant nearby, we went to Silver Lakes, California, and also Barstow. We went armed with very large posters with pictures of the technology so that we could not only solicit their opinion, but also begin to educate the public. And what we learned was that 90% of those surveyed were either positive or neutral about solar energy in general. They were generally more positive about the aesthetics of the tower, like we learned at Tonopah. There was a preference to develop in disturbed desert land, but there was an acceptance for developing or for solar development in vacant desert, undisturbed vacant land. And the majority did say that they would support future CSP development. Next slide, please. So, just taking a broad overview of these three communities, it's very difficult to compare them because they have very different lived experiences. And also the survey instruments evolved as we talked to more people. But what we do conclude is the majority of people surveyed do view solar energy positively and support future developments. Again, they prefer development on previously disturbed land, desert land, or there is also an acceptance for vacant desert land. The aesthetics were not an issue of the solar towers, and it is crucial, and this was expressed in all three communities, that any local solar project be owned by a U.S. company, employ local workers, and source materials from U.S. businesses. And I am going to turn this over to Hank to wrap this up.
Right. So going back to our original question, is there a role for CSP in California? Christina? The answer is yes. Our take on it is yes, there is an opportunity. Obviously, that'll depend on the cost and a lot of factors, but we wanted to identify which configurations made sense. We believe molten salt tower is a commercially mature technology. New plants are reliable and cost competitive with the alternative, which would be PV and batteries. Configurations can be designed to be either base load or for night dispatch scenarios. We found a number of sites within California, within the CAISO service territory boundaries that we think are likely to be economic, so potentially 5 to 10 gigawatts of potential capacity. And there was substantial capacity outside of California, Arizona, New Mexico, and even Nevada, if transmission exists into the state to carry that power. Finally, how do you reduce the costs? Hybrid plants with using PV or building power parks with multiple plants can help drive the cost down to be even more competitive. A lot is going on in California right now with their planning for SB 100. And so there are a lot of areas where CSP could be integrated into that planning process to help CSP be deployed in California. As we saw, as John mentioned, CSP was not included in their early modeling. And so we really need CSP to be included in the resolve modeling that California uses for doing their capacity expansion studies. That's similar to what Alex showed you from the RPM model from NREL. CSP should be, the good resource potential areas should be considered in the transmission planning process. And we need CSP to be included in their new IRP process. We need California to develop the way of calculating the marginal effective load carrying capacity for CSP plants. So in summary, we think there is an opportunity for CSP moving forward, and we're hoping to continue the dialogue with the state of California to encourage them to include CSP in their planning as they move forward. I think that concludes our study. You have our contact information here, and now I guess we're open for Q&A. Christina?
Correct. Well, thank you so much to all of you. A great presentation, a lot of information. So let's try to see if we can get to as many questions as we can. If not, however, we will send to our panelists the questions. Just a reminder, Allison also mentioned it, we will share with you the slide deck, the materials, as well as the recorded webinar. So I'm going to start with a question that Hank, you wanted to answer, and you did mention it a little while earlier. So we're going to start with that one. However, it's directed to Hank, but if any one of you wants to also add anything, just let me know, or just speak after Hank's answer. So Hank, how does the NREL RPM model choose the optimal number of hours of storage? Does the optimum change over time, or what is the crossover point compared to BB plus batteries?
Sorry, I meant for Alex to answer this one.
Okay, Alex.
Sorry, I'm flipping through the other answers. This is the RPM model from Mark's question?
Yes,
Yeah.
Mark, my host. Yes,
Yeah,
correct.
yeah, certainly. So we actually we had a collection of about 8 different configurations that vary by solar multiple and thermal energy storage duration. We did some initial screening to avoid things like, anything that was against the hypothesis, which was that we would be providing nighttime dispatch. So nothing without thermal energy storage was considered. And then from there, using some prior techno-economic analysis, we kind of had some bounds on what we thought, from at least a levelized cost of energy perspective, and the ability to meet that key nighttime dispatch, sort of min and max sizes of the plant. So we have all 8 of those configurations placed in RPM, and RPM chose it for us. So that 3 solar multiple 12 hours of storage, while it was just part of a discrete collection, that happened to be the most popular one. There were also some other deployments that happened outside of California. I think there were some smaller ones from that. And I'll also note that I think Hank's study had a 14 hours of storage, so it wasn't a perfect match. But we kind of had an idea of what the best design would be, at least in that discrete collection that turned out to be the consensus from our capacity expansion run.
Yeah, I would point out, our expectation was that the model would pick. I mean, my expectation was that the model would pick the night dispatch, and so we were a little surprised that it picked the baseload configuration otherwise. And I think it makes sense because it's just showing how important it is that you're able to deliver power at night and meet that ramp that Alex highlighted.
Great. Anyone else would like to add to this question?
No,
Okay,
let's go.
let's go to the next one then. Okay, this one's for all of you. Hank, I know you marked it as well, but whoever wants to, please feel free to answer. So it goes this way. How can CSP fit with the current energy policy?
Can I take a stab at that, Hank?
Yeah, please.
I'm reading from the President's executive order, in which the United States wants affordable, reliable, dispatchable domestic energy not controlled by foreign adversaries. CSP is that. It is dispatchable, it's reliable, it's not controlled by foreign adversaries, and I think we simply have to present it as long duration, reliable, long duration energy storage capable of providing reliable energy, domestic, and I think we will be okay. I hope. Anyone else want to add to that?
Okay, perfect. Hank, did you want to say something? You're good?
No.
Perfect. Well, thank you, Fred. Next question. Alex, you marked it. However, as the same, whoever wants to reply, please also do. Sorry, it went up. Now that the cost of electrochemical batteries are falling rapidly, what is the place of CSP in the power system?
So I can opine on this just because I recently joined the team for the annual technology baseline. There are learning rates associated with the different technologies in the ATB, and there are forecasted cost reductions that come with that over the course of time. So we did adopt a learning rate, and there were cost reductions that took place for batteries, in addition to CSP, PV, and the other technologies as well. So I'll claim that those were baked into the study back using the 2022 assumptions. Those get updated every year, and there is market tracking and so forth. And so, if we reran this study using sort of a new cost curve, we might get different results. The question as to whether battery prices are falling in concert with what was forecasted, that's something I don't have an immediate answer to. But if I think looking back at the 2022 ATB versus how costs hash out today, I'll probably tell you that answer.
I would also like to add that the IRENA study done a few years ago noted that CSP is at the top of the learning curve, 8 gigawatts globally. And it's come down faster in price than PV did in its first 8 gigawatts. So there is a lot of cost reduction that will come as we ramp up. So I think that's another element of the PV batteries versus CSP cost picture.
Perfect. Well, thank you. Next question also marked. What are the mechanisms behind the avian mortality associated with CSP plants? Moreover, what sorts of design technology improvements led to reduced mortality rates? Go ahead,
I'll take
Hank.
that. Okay, so first of all, there have been avian mortalities at CSP tower plants. It is a topic of concern that the industry is taking very seriously. That being said, a lot of what's in the media is either exaggerated or sometimes just incorrect about what's really occurring at the plants. Ivanpah is kind of the center of attention and has done the most work to try to understand the real problem and has tracked it over time, and has implemented a number of strategies to reduce that. There was a key operational strategy that significantly helped reduce the impact early on in the plant when it first came online, and all new plants are implementing that strategy. Basically, the main issue is high flux zones in the air that birds aren't able to perceive, and they potentially fly through it. And so the key change has been to minimize these high flux zones that exist above the plant when it's in operation or not in operation. You normally have to aim the heliostats and to make sure that there's not glare issues, and we've just learned that we need to do that better. The tracking, so they've implemented a number of strategies to try to scare birds away from the receiver, which is the other area where there's high flux potentially. And there's a lot of new ideas that are using AI to detect birds so that they can defocus mirrors. That isn't yet developed. But it's important to note that they do annual surveys at Ivanpah, and the biologists doing the studies indicate that the impact to the local bird population is low, both for local and migratory birds passing through the area. So it is an issue, just like it is an issue with wind turbines, and it is on sort of a similar magnitude. So it isn't super extreme, but it is an issue that has to be considered.
Perfect. Well, thank you. I think we have time for one more question. So last one, whoever wants to respond. How do you respond to the point that few, if any, countries have continued with CSP? They do a few plans and then they stop. Why is that? Who wants to answer? Fred, go ahead.
I would say the same reason it stopped in California for a while. PV got very cheap and they didn't value storage. They were okay with a few hours of storage, but night happens and they care about it. So I think that they're going to take the same look that we hope California will take a look at. And if they want to value carbon-free dispatchable energy, they'll do it. The plant in Dubai, the last one that was built, the requirement was carbon-free 24/7, and they couldn't do it with PV and batteries alone. So I think it's just the realization that yes, PV is cheaper than CSP, and it always will be for the daytime, but they complement each other, one in the daytime, the other at night, if they value that.
Yeah, I would add that the premise isn't quite true anymore. In China right now, there's a massive build out of CSP molten salt tower plants. And at this point, it looks like that's not stopping anytime soon.
Perfect. Well, thank you very much. Is there anyone else who wanted to make a contribution? Okay. Well, we have a couple of more questions left, but since we're already out of time, we will send them to our panelists. Allison, Fred, Hank, Alex, and John, thank you so much for an amazing presentation, helping us figure out a little bit more of the California's puzzle and seeing that CSP does have a space there. And I would like to also thank all the people attending. It's great to see familiar, well, I would say faces, we can't see you, but familiar people who have attended previous webinars and have spoken. So thank you so much for great questions, to keeping the webinar and the session very interesting. We hope to see everyone very, very soon, and we hope you all have an amazing day. So thank you very much, everyone.
Thank you, Christina.
Have a great day.
Thanks a lot.
Thank
Thank
you.
you.
Bye.